Well, I think we can go ahead and get started. Thank you, everyone, for coming to the LPI virtual seminar this week. Our guest this week is Dean Denton at Purdue University. I actually met a dean here at LPI back in 2015 when I was a CLSD intern, and she was doing undergraduate research with David Krink. So I've been following her career with interest, which she will be talking about today. So I wanted to remind folks about very quickly, please leave your microphones muted and your cameras off during the talk. If you have questions during the talk, please feel free to type them into the chat. We'll address them in the last 10-15 minutes of the talk. With that, thank you so much for coming, Adine, and please take it away.
Thank you, Sean, for the introduction, and good afternoon, everybody. It really is really exciting to be back at LPI because I did definitely start my planetary science career in 2015 when I was an intern here. And funnily enough, David Krink had me studying meteor craters, so I just said, wow, I really enjoy craters. I would just like to go bigger and bigger from there. And now we're here. So I'm Dean Denton, and within the realm of planetary science, I'm what you might call an impact physicist. My work uses the unique properties of impact basin formation and evolution to repurpose giant impacts into a tool that we can use to probe the interiors of icy worlds across the solar system, to search for oceans, investigate core compositions, and more. And today I'll be sharing with you some of my work on Pluto, everyone's favorite former planet, and what we can learn about it by taking a closer look at some of its largest impact structures. And I'm going to begin this talk by refamiliarizing you with the exoplanet itself. Though before I start, I will note if I have any technological issues that I do not notice, please let me know. Just unmute and let me know. And I will not be able to read the chat while I'm talking because I simply am not talented enough to speak, read, and think. Thank you for your patience. So, before 2015, all we really knew about Pluto were the large-scale brightness variations visible from the Hubble Space Telescope that were taken in 2003, and they yielded this nice rotating blob. A huge improvement from when Pluto was just a pinprick of light in the sky, but not so good for any kind of geologic observations. We simply didn't have the technology to get a closer look. New Horizons flyby in 2015, however, completely transformed our understanding of Pluto and Kuiper Belt objects as a whole. The surface of Pluto that emerged following the flyby is incredibly complex, covered in widespread geologic activity, including extensive glaciation by volatile nitrogen, methane, and carbon monoxide ices that carve into mountains made of water ice, as well as globe-spanning troughs and scarps. But the surface is dominated by the elliptical basin known as Sputnik Planitia, often referred to in the media as Pluto's heart, that's at the center of this image. Now, due to its large size, elliptical shape, and low topographic signature, that is the fact that it is a giant hole in the ground, scientists have suggested since its first observations in New Horizons data that Sputnik Planitia is a massive impact basin, one that covers about 15% of Pluto by surface area. Additionally, its current location and relationship to local tectonic features is one of the primary points of evidence for persistence of a subsurface ocean to the present day. As such, Sputnik Planitia is intimately tied to the evolution of Pluto's interior, but our overall understanding of the history of the basin and its global influence on Pluto remains unknown. It's one of many questions that we still have when it comes to the overall history of Pluto. And what we do know about Pluto after New Horizons is maybe both more and less than you might think, because filling in the gaps always leads to more questions. So with that in mind, I'm going to start from the bottom of a cross-section of Pluto and work my way up, discussing what we do and don't know about Pluto's interior. So I'll start with the core. Well, the size of Pluto's rocky core is actually decently well constrained from estimates of Pluto's radius, its density, and assumed differentiation, which places it at a little over 2/3 of Pluto's total radius. But its composition, however, remains unknown. Thermal evolution models have suggested that Pluto's core may have retained significant porosity or have experienced extensive hydrothermal alteration early on in Pluto's history. But neither of those features is something that can really be detected from surface observations, so any qualitative information about the core remains unknown to us. Moving upward, we get to a fun question. Does Pluto have a subsurface ocean, or did it have one in the past? Several lines of evidence point to yes, including the lack of a fossil bulge in Pluto's shape, suggesting that Pluto's ice shell didn't get frozen in earlier, as well as the presence of widespread extensional tectonics that were mapped here by Keene et al. In 2016. And these are interpreted to be at least partially the result of global expansion from an ocean freezing. And lastly, the location of Sputnik Planitia itself near the Pluto-Charon tidal axis, which is shown here in red, has led researchers to infer that the basin is what's known as a mass con, or a positive mass anomaly, meaning that at this location, we think there's more mass than there should be, which is pretty unusual because to create a positive mass anomaly in an impact basin is non-trivial, because the missing mass, that is, when you make a hole in the ground, we're actually removing material, so there's missing mass in this impact basin. That means that that missing mass needs to be offset by dense material, and in this case, that dense material is inferred to be two things. First, the nitrogen ice load on the surface. That is the white material that currently fills Pluto's heart and makes it look so nice. That's a load of nitrogen ice. But it's believed that that nitrogen ice is combined with an uplifted ocean beneath the basin to make the positive mass anomaly. And that theory suggests that the ocean needs to persist to the present day in order to keep this basin where it's currently at. So it's worth noting that each line of evidence that I just stated can potentially be associated with an alternative geologic process. However, taken together, both theoretical and observational efforts strongly favor the presence of an ocean beneath Pluto's ice shell. But the relative size of that ocean and any of its other characteristics remains uncertain. And you may have guessed it, that's an ongoing theme. Lastly, Pluto's ice shell. We know from New Horizons that Pluto's uppermost layer is likely pure water ice with a thin veneer of surface volatiles. That's best exemplified by the several kilometers of nitrogen ice that's currently filling Sputnik Planitia. But the thermal and mechanical structure of that ice shell remains unknown. If Sputnik Planitia is a mass con, if we believe the theory that I introduced on the previous slide, then thermal models suggest that Pluto's ice shell should be primarily a stiff conducting lid in order to preserve the topographic variations in the basin over geologic time and prevent viscous relaxation. The thickness of that ice shell, however, as well as what thermal structures are possible within that conductive framework, have remained relatively unconstrained. And that's what we know about Pluto's interior. There are so many uncertainties in basic interior properties, including what the core is made out of, whether or not there's an ocean, and how that affects the overlying ice shell. But fortunately for us, all of these are testable parameters that we can investigate. And these major properties have yielded some of the major remaining questions following New Horizons. In particular, could Pluto have sustained an ocean? The evidence is there, but it's largely circumstantial. Did liquid water interact with Pluto's core? Or to put it another way, which might make more sense why we'd love to know this so badly, could water-rock interactions have taken place in Pluto's interior that left the whole planet chemically transformed to potentially a suitable place for life? And lastly, how thick is Pluto's ice shell really? And how is it structured? Is it completely cold and stiff, or is part of it more readily deformable? These are all vital questions that, despite all the new information that New Horizons provided, we still can't answer for sure. And for me, at least, all of these many questions boil down to one fundamental question that motivates me in my research, which is, what is the thermal and mechanical structure of Pluto? And how has it evolved over time? Now, that's a pretty big question, but fortunately, we can use a giant impact to take a look inside Pluto, or smash right through the planet, as the case may be. So this is where Sputnik Planitia comes in. Because the morphology of large impact basins like Sputnik Planitia is dependent on the thermal and mechanical structure of the subsurface, meaning that the presence, morphology, and overall longevity of Sputnik Planitia, everything about how it looks today, as well as its role as a potential mass con, directly reflect Pluto's thermal and mechanical structure at the time that the basin formed. So that leads us to the hypothesis that governs both the work that I'm sharing with you today, as well as my future projects, which is the theory that we can use giant impacts to inform our understanding of both thermal and mechanical variations in planetary interiors, including, in this case, Pluto. Now, starting from this initial goal, what I'm going to do is cover two ways that we can use impacts to take a look at planetary interiors, by breaking down the influence of giant impacts into their proximal or their near field effects in the immediate vicinity of the impact basin, and their distal effects or their far field effects that take place much farther away. And first, I'm going to revisit the initial formation conditions for Sputnik Planitia to look at the proximal effects of impact. That is, how the thermal structure and the thickness of Pluto's ice shell influences resulting basin morphology, both at the surface and at the ice shell interface. And then I'm going to consider how the influence of impact itself may have stretched across the entire planet, looking at how potentially distal effects like antipodal focusing can drive long-range tectonic deformation. So I'm going to begin by considering Sputnik Planitia's formation directly, because based on the theory that I'm working from, I'm wondering which thermal and mechanical conditions in Pluto's interior produce basins consistent with Sputnik Planitia as we observe today. And that means revisiting the basin's formation conditions to look at what factors influence the size and shape of Sputnik Planitia. Can we reproduce it? Well, it's worth asking, why am I saying revisiting? Well, why are we revisiting the formation conditions? It's because the basin was indeed modeled before, but under vastly different interpretations of both the ice shell's thermal structure and estimates of basin size. So those earlier simulations were performed using earlier, smaller estimates that were made immediately following New Horizons' initial encounter and prior to in-depth analysis that took place in the subsequent years. The newest highest resolution estimates from Schenk et al. In 2018 placed the full size of the basin at around 1,200 by 2,000 kilometers, almost double the initial estimates that were previously used. Schenk et al. Also re-estimated a shallower basin interior by 1.5 to 2 kilometers. And those are pretty significant changes in how we think of this basin. And because basin structure and its relationship to planetary interiors can change quite drastically with size, these significant changes in morphology could indicate drastically different pre-existing conditions in Pluto's ice shell. So that means it's time to figure out once again what formation conditions produce Sputnik Planitia as we see it today. Now to do this, I have built a small army of Plutos, all with varying internal structures. I then simulate the Sputnik Planitia forming impact into these test planets to watch what happens and see if I get a basin that matches the estimated size and shape of Sputnik Planitia with reasonable pre-impact conditions for Pluto's interior. And the resulting impact simulations look like this. I'm sorry. No, they don't. They don't look like that. They're actually a bit less complicated than that, which is good for me. But I would still like to explain to you what it is I do to simulate the Sputnik Planitia forming impact. Well, to adequately simulate a basin forming impact, I use the ice sail shock physics code, which is a code that's designed specifically to deal with the conditions endemic to hypervelocity impacts. And in designing my simulation of Pluto, I began by following a setup that was initially similar to those first tests done in 2016. There's no real reason to reinvent the wheel in some ways, especially when it comes to the initial design of Pluto. So in particular, I'm simulating Pluto as a 3-layer target. So that means I'm using a rocky core for Pluto's core, a water ice shell to simulate Pluto's ice shell, and where present, I'm using a liquid water ocean for Pluto's ocean. And I'm also using what's called a central gravity field because of the size of Sputnik Planitia. Now, if you've seen impact simulations in the past, which you may have, a lot of them are impacts hitting a flat target. Not so in this case, which is why I'm showing you 2 of my pre-existing conditions for Pluto's interior at the bottom. I'm simulating Pluto as a spherical target because the size of Sputnik Planitia relative to the entire planet means that the curvature of the planet actually influences the resulting morphology of the basin. So in central gravity, Pluto is simulated as a sphere, and gravity is calculated radially so that it varies with distance from the center of the body to account for density changes in Pluto's interior that affect the materials. And I'm simulating the regions surrounding Sputnik Planitia with 2-kilometer spatial resolution so that I can capture the resulting basin. And the impactor that hits Pluto does so using the inferred average impactor speed of the Kuiper belt, which is 2 kilometers per second. And any impact scientists in the audience might be thinking, wow, that's really slow. Impactor speeds in the inner solar system and even at the giant moons are much faster. Well, welcome to the Kuiper belt. Things move a lot slower out here. That was the initial setup. But we also had to update things quite a bit, which is what I alluded to. So first, we had to update the impactor size in conjunction with updated basin dimensions. And that ultimately almost doubled the resulting impactor size to around 400 kilometers, which is about the size of Saturn's moon Mimas, if anyone's counting. Additionally, we use a nonlinear thermal gradient to reflect the highly temperature-dependent thermal conductivity of ice, and thus more accurately simulate the thermal structure of Pluto's ice shell and its influence on ice shell strength. Then we investigated the different interior structures for Pluto that we think might influence basin morphology. And in particular, we focused on the 2 most critical unknowns. That is the presence and thickness of an ocean, which correlates to a thinner overlying ice shell, and the thermal gradient in that ice shell, which might vary quite significantly. I'm showing 2 potential interiors that we used below that incorporate that nonlinear thermal gradient, though in each case, we are assuming that that ice shell is fully conductive. And I'm varying the presence of an ocean between no ocean at all and a relatively thick ocean, so 150 kilometers thick. Now, to balance examining a wide range of thermal gradients with making sure they're within the realm of realism, we applied thermal gradients that, for each ocean thickness, kept the ice shell cold enough to prevent relaxation of the basin over geologic timescales, because we're still focused on whether we can produce a basin that's consistent with a mass con, but also keeping the ice shell warm enough to permit an ocean beneath. And at Pluto, that actually incorporates some pretty cold options. Now I'm going to walk us through some of the most important results from these tests and their implications for the formation of Sputnik Planitia. And first, I'm going to show you a video of the Sputnik Planitia forming impact, a real one this time, using the newer, larger impactor, which you can observe at the top of the image. Now, this video represents what is, for Pluto, a medium to cold thermal gradient of 1 Kelvin per kilometer, and a relatively thick ocean of 150 kilometers. And I'm plotting two things in this video for comparison. Temperature is shown on the left in Kelvin, and I'm plotting material on the right. So I have ice in white, and both the ice shell and the impactor are ice. And below that, I have a light blue ocean. And at the bottom, that dark blue is Pluto's core. With that in mind, let's take a look at this video, and we can see that large impactor is moving so slowly that it forms this cold layer in the interior of the transient crater. That transient crater starts to collapse. That inward collapse drives the formation of a massive central uplift. That central uplift then oversteepens and collapses, and the warm deforming ice that makes up the central uplift spills out over the rim of the pre-existing transient crater and onto the surrounding plains of Pluto. Now, now Sputnik Planitia is quite large, which means it's not quite done forming. There's a second period of inward collapse and formation of a second, though smaller, central uplift. That central uplift then also oversteepens and collapses. And it ultimately takes about 4 to 6 hours, depending on model parameters, for the final basin to form. And the final basin looks like this. This is the resulting morphology for one of our best fit cases to the basin. And some items of note. We have produced a basin that possesses a broad zone of thinned ice in its interior, which is causing an uplift of the ice shell ocean interface and thickened ice under the basin rim. And this is the kind of structure we'd expect if Sputnik Planitia is indeed associated with a positive mass anomaly. Thinning the ice in the interior of the basin relative to its pre-existing thickness means that there is more ocean underneath the center of the basin than elsewhere. And to place what I'm showing you here in context, the specific basin in the context of the tests that we performed and the variables that we tested, that is ocean thickness and ice shelf thermal structure, some of the broad scale results from this work were as we expected. That is, increasing the impactor diameter increases the size of the basin to the right size, which is thrilling, but it also increases the ice shelf thickness fluctuations relative to the basin size, meaning that this interior zone of thinning that I've produced here is much, much larger than any previous runs. And in terms of mechanical variations, so the role of the ocean underneath the ice shell, the results are fairly intuitive, meaning a thicker ocean and a thinner ice shell produce a wider basin and greater ice shell thinning within that basin, while a thicker ice shell is stronger and more readily resists extensive deformation. However, we also found that in addition to mechanical variations that are driven by the ice shell ocean contrast, thermal gradient is also a first order control on basin formation, though it is a subtler one. So for a given ice shell thickness, increased thermal gradient yields decreased basin depth and reduced ice shell thinning, decreasing the contrast at that ice shell ocean interface, and thus potentially reducing the possibility of a mass-con because there's less ocean underlying the basin, though it's not eliminating the possibility entirely. The key point here is that the thermal structure of the ice shell appears to exert a first-order control on basin morphology in addition to the mechanical structure, which means that going forward in our consideration of these large basins formed in ice, it's not enough to just place bounds on ice shell thickness. We also need to pay attention to the body's thermal history. We know that the thermal structure of the ice shell affects basins at the smaller scale, but it also influences basins at the absolute largest scale, which is quite fascinating, really. So that's the proximal side of things. We've nailed down Sputnik Planitia's initial morphology and the interior properties that define it, at least broadly speaking. And what I've found is that to produce a basin that approximates both the size and shape observed at the surface, as well as the inferred subsurface structure necessary to produce a mass-con, that is, the uplifted ocean underneath the ice shell, Pluto's ice shell needs to be underlain by a relatively thick ocean and possess a thermal structure that falls in the middle of the ranges that have been previously proposed. Too cold and the ice is too strong. Too warm and the relatively weaker ice eliminates large-scale topographic variations. So in investigating the proximal effects of Sputnik Planitia's initial impact, that is the actual basin morphology itself, what we've learned quite a bit about is the properties of Pluto's uppermost layer, that is this ice shell. But we can actually keep learning quite a bit more about Pluto, which means I'm not done blowing it up just yet. I will now address the second aspect of this talk, which is distal deformation, impact-induced effects that take place much farther away from the impact point than just the basin rim. And to consider that, we'll need to look at the global context of Sputnik Planitia in a new way. So here I'm showing a global mosaic of Pluto that's centered on its far side, meaning that Sputnik Planitia, which was centered at the center of the image in all of the previous images I've shown you, is now at the edges. There it is. And what we can observe upon taking a look at Pluto's far side is this unusual region of disrupted and lineated terrain that's around 1,000 kilometers in diameter. Now, because this terrain is roughly antipodal to Sputnik Planitia, and by antipodal, what I mean is that if Sputnik Planitia is one point on the surface of Pluto, if we draw a line straight down from that point through Pluto's core and out the other side of the planet, that point is Sputnik Planitia's antipode. Now, because this terrain is roughly antipodal to Sputnik Planitia, it raises an interesting question of correlation and causation. And that may be initially surprising because these features are as far away as it is possible to be while still on the same planet. But antipodal terrains are actually known to be produced in association with planetary scale impacts. And they've been observed at the antipode to Caloris basin on Mercury and Imbrium on the Moon, where they produce hilly and lineated surface features as a result of focusing of the seismic waves released from the impact point. Basically, the initial impact acts as a point source, seismologically speaking, and as seismic waves expand hemispherically through the body, they tend to be focused by planetary geometry such that they converge at the antipode. This is an imperfect analogy, but it's similar to how when light enters your eye, the geometry of your eye acts as a lens to focus that light to the back of your eye so that it reaches your retina. Similar things are happening here. It's just on a planetary scale. And the fun thing about the possibility for antipodal deformation from large impacts is that similar to impact basin morphology, the magnitude and extent of the deformation that occurs at the antipode to a large impact is highly dependent on the internal structure of the target body, which is great for us. That means we can test it doing some of the crudest seismology it's possible to do. My work uses simulations of the Sputnik Planitia forming impact to determine whether Sputnik Planitia can actually generate the energy required to disrupt the surface on the scale that's been observed on Pluto's far side. And from there, think about what the resulting behavior can tell us about the internal structure of Pluto. Well, to do that, we're back with ISAIL. And I'm using a similar setup to the previous work that I just discussed. Only this time, that 2-kilometer resolution zone that I was using in the proximity of Sputnik Planitia is now being extended to the entire body to adequately resolve deformation at the antipode. We are zooming out because now the entire planet is important and of use to us. And I'm also using that same updated impactor size and nonlinear thermal structure because in simulating antipodal deformation, we do want to be accurate about the basin that those waves are coming from in the first place. So now that we've defined Sputnik Planitia proximally, we can use those same conditions to look at the far field effects of the basin and be content that these two features, if they're both formed, match their real life counterparts as best we can. And we then vary the two unknowns in Pluto's subsurface that are most likely to affect antipodal focusing. And those are ocean thickness and core composition. So I'm varying ocean thickness similar to how it was varied before. That is, I'm starting with no ocean at all, and then going to a relatively thick ocean, so 150 kilometers thick. And I'm varying core composition between a core that hasn't experienced hydration, approximated by a dunite core, and a core that has experienced significant hydrothermal alteration. And that's approximated by a serpentine core. And I'm now going to walk us through some of the initial results from those tests and discuss their implications for the formation of antipodal terrains and also for Pluto's interior writ large. And I'm going to begin with a GIF of our best fit case. Our best fit case includes a 150 kilometer thick ocean and a serpentine core. And I will show you why that's the case. But first, let's just take a look at this GIF. So in this GIF, material is colored according to target velocity, and that allows us to observe the transmission of waves through Pluto's interior. It's a proxy that allows us to see those wave fronts and how they get passed to the antipode. Now, in this image, the ongoing formation of Sputnik Planitia is at the top, and the antipode is down at the bottom. And what we're interested in is the process that's going on in the interior between those 2 points. And if we wait for the GIF to restart, we can see that initial wave getting propagated through the interior, where it is then focused to the antipode. But there's a lot going on in this GIF. It's a pretty complex process, which is why I've also broken down that GIF into a time series so that we can focus on specific things that are happening. Everything happens very quickly in the earliest stages of basin formation. So in this first frame, we can observe that initial transmission of the P wave and the S wave from impact through both the core and the ice shell. But the compositional variations between them are separating the wave in the core, which is traveling faster, from the wave in the ice shell. And as we step forward in time, the wave in the core is focused to the antipode, while it remains delayed in the ice shell, where it's actually isolated from the core by that liquid ocean that's separating the two, such that it ultimately takes another 400 seconds for the wave in the ice shell to arrive at the antipode, effectively producing a second high velocity pulse. This general trend of separation between the ice shell and the core is something that we observe in all of our runs. However, the presence of an ocean and the composition of the core both have clearly observable effects on deformation, which I'm now going to discuss. And I'm going to do it using strain as a proxy. When it comes to visualizing what's actually happening at the antipode, after stress wave arrival and extending that to whether or not deformation occurs, we can interpret elevated strains as a proxy for where and how that deformation might happen. Now, the plot on the right shows strain experienced in the ice shell at 10 kilometers depth, measured outwards from the antipode, which is at the origin. And I'm using strain in what's called the theta-theta direction, or measured along constant lines of longitude. And for those interested, one way to visualize this might be if you think back to the cross-section of Pluto I've been showing you, it is along the curvature of the planet. And I'm using that component because it's the component with the largest magnitude in our simulations. And in our formulation of strain, positive strain indicates extension, so the ice shell getting pulled apart, and negative strain indicates compression. And the extent of the resulting strain is something that we can then compare with the radius of the lineated terrain. So that's shown there at the bottom. And here I've plotted one of our most basic cases, which is no ocean and a serpentine core. So that's just ice overlying rock. And what we can observe from this initial case is that a clear zone of extensional strain is established in the region surrounding the antipode. But what I'm about to show you is that the magnitude and extent of the extension zone is dependent on both the presence of an ocean and ocean thickness. So when a thin 50-kilometer thick ocean is first added, and that's here in cyan, overall strain is massively reduced. And there's a physical basis behind this reduction. The addition of a liquid low velocity layer between the core and the ice shell adds a sudden increase in impedance contrast between materials. And that contrast reduces transmission at the core ocean boundary. So more energy is reflected back into the core instead of transmitted to the antipode. And that's something that we can notice just by the contrast in sound speeds, which I've listed on the bottom left. However, this dampening effect that ocean has on strain and thus on deformation is something that starts to change as ocean thickness increases. So here is an increase with a 100-kilometer thick ocean, shown here in yellow, but we still haven't reached pre-ocean levels in terms of strain. That all changes when the ocean is very thick. When we hit a 150-kilometer thick ocean, shown here in pink, the strain is actually massively increased. This is because of a corollary effect that the ocean also has. So the dampening effect on energy from the core is still in effect. The ocean still does do that, but it's offset by the effect of a thin ice shell overlying that thick ocean. When the ice shell is very thin, energy transmitted through the ice shell is effectively concentrated in the near surface. The ice shell acts as a waveguide and enhances antipodal deformation. So thin oceans damp out strains at the antipode, but large oceans actually enhance them. And in this case, we can also note that the elevated strains for our thick ocean case are consistent with the estimated extent of the lineated terrain that's been observed. But that's not all that's going on here. Let's talk about the other piece, which is core composition. The effect of core composition is actually more straightforward than that of the ocean. So here I am plotting no ocean cases. So just ice overlying rock. And a dunite core is in white and a serpentine core is in cyan. And we can observe that a serpentine core that's lower density, we can observe that a serpentine core produces greater deformation at the antipode. And that effect is because changing the composition of the core changes its sound speed. So a serpentine core is lower density. And that lower density means it has a decreased sound speed relative to a dunite core. And that decrease in core sound speed reduces the contrast with the overlying ice. So more energy gets transmitted from the core to the antipode. And that's what's driving the difference that we can observe in this plot. And that trend holds for all ocean thicknesses. Here is the same comparison for a 150-kilometer thick ocean, where the difference is even more dramatic. As such, a Pluto that has both a thick ocean and a serpentine core, and that's plotted here in cyan, maximizes antipodal deformation by maximizing energy transmission through both the core and the ice shell. And that is the case that maintains the correct extent of deformation from the antipode to match the estimated region of deformation that's been observed. So that's great, but now we need to get back to the actual geologic evidence and ask, well, what kind of features would this kind of deformation produce at the antipode, and are those realistic? Can we link this zone of elevated strain that I've produced in my models to what we're actually looking at on the far side and extrapolate to what we might expect to see? Well, the strains of our models are extensional. So if we extrapolate from that, then we would expect to get graben. And we can estimate the depth of those graben by considering the average strain in our models as being distributed across the diameter of the terrain that's been observed and accommodated by between 2 to 4 graben surrounding the antipode. Now that number of graben is a rough estimate based on the available data, and for reference, those lineations are shown here on the left. If we do that, we get graben depths of between 2 to 3 kilometers, which are similar to, though slightly larger, than the massive graben that have been observed on Pluto's near side, like Virgil fossae, shown here on the right. So this image gives us a sense of what it might look like if we do return to Pluto, and I sure would love it if we did, and got a second look at those far side lineations in more detail. The key point here, though, is that we can produce those antipodal terrains from the Sputnik Planitia forming impact, but to do it, we need both a thick ocean and a hydrated core. which in turn implies that despite the inhospitable surface conditions, Pluto and Kuiper Belt objects like it might possess incredibly active interiors, and thus the potential for life. And to zoom back out, I would like to talk a bit about the bigger picture that we can draw from the work that I've shared with you today. So I began by looking at proximal impact-driven deformation. That is the deformation that's concentrated in and around the basin. And what I found was that both thermal and mechanical variations are primary drivers of the basin morphology, which means that we can use the proximal effects of giant impacts to probe these broad upper-level characteristics of the outer shells of icy worlds. And if we move outwards to consider distal effects, I found that antipodal focusing was dictated by much deeper influences within Pluto, including the presence of the ocean and the composition of the core, which means we can use the same impact's distal effects to look deeper into planetary interiors. And combining these two together allows us to probe the interiors of icy and ocean worlds at a variety of scales. And on Pluto, what that might mean is combining these techniques suggests that Pluto could have an interior that's much more active than previously anticipated, which is a change in our interpretations of its interior evolution that might influence how we look at Pluto and other Kuiper Belt objects. There's just so much we can learn if we properly apply one impact to a planet. But fortunately, there's not just one giant impact in the solar system to choose from. There's other impacts that we can use to take this theory, extrapolate it, and test it in more detail. And in some cases, we don't even have to leave Pluto. So I've talked about Sputnik Planitia quite a bit. This is a projection of Pluto centered on Sputnik Planitia, and this is topography, with low being purple and red being high. Oof, that was a weird way to say that. So low is in purple and cool tones, and high is in red. So that means that Sputnik Planitia at the center of the image is this big purple low, and the distributed red surrounding it is its degraded rim. Now that's Sputnik Planitia, and it is Pluto's largest impact basin, uncontested by a large margin. And it's very interesting, and I love it very dearly. But let's talk a little bit about Bernie, which is Pluto's second largest basin and happens to lie just to the northwest. Now, Sputnik Planitia is a large impact basin that has one coherent rim. What's interesting about Bernie is that it appears to have rings, multiple rings, in fact, suggesting that Bernie might be what's called a multi-ring basin. That is, instead of having one coherent rim, it appears to have a series of concentric rings. And that's pretty interesting because multi-ring basins have been observed in the outer solar system, and they've been primarily studied on the moon, where, they've been primarily studied on the moon because we've got great data from the moon. And the best example of a multi-ring basin is Mare Orientale, shown here on the left. And studies of how multi-ring basins like Orientale form indicate that multi-ring basins in particular within impact basins as a feature class are very strongly dependent on the thermal and mechanical structure of the lunar crust and mantle in this case. And so what we believe occurs during multi-ring basin formation is during collapse of the basin, the inward flow of the mantle exerts drag on the stiffer overlying crust, producing large normal faults, which are then expressed at the surface as concentric rings. And that is what we interpret to be looking at in these multi-ring basins. Now, that's on the moon. Well, Orientale and Bernie do share some strong morphologic similarities, which in turn suggest similar formation mechanisms, that these are both potentially multi-ring basins featuring large normal faults in the crust. But that implies some unusual things about Pluto's interior, because Pluto doesn't have a mantle or a crust. It has an ice shell and potentially an ocean. So that means the ice shell needs to pull double duty as both that cold, stiff crust and a more readily deforming mantle, which implies a potentially much warmer ice shell than that which has been currently inferred at Sputnik Planitia. So I'm currently doing some simulations to try to reconcile what Pluto's largest basin and Pluto's second largest basin might be telling us about Pluto's ice shell and its thermal history. And I look forward to updating you all on that in the coming months. But to look beyond Pluto for just a minute, there's really not just one giant impact in the outer solar system. They happen to be many. So looking at giant impacts offers us a tool to examine many of the worlds in the outer solar system from the inside out, going back to some of these icy bodies that we want to look at in more detail and probing beneath their surfaces. And in particular, just an example of how we might be able to use this, I'd like to talk about the Saturnian system, because the diverse interiors and evolutionary histories of Saturn's mid-sized moons in particular really provide the perfect natural laboratory to investigate this link that we've identified between basin formation and the interior properties of icy bodies. And we can do that at a range of scales and with a range of interiors. So Mimas, the closest and smallest of Pluto's mid-sized moons, is dominated by Herschel, the basin on the upper right, which is of course what makes it look like the Death Star. And it has what might be an unusual interior. It could host either an asymmetric elongated core or a possible subsurface ocean, both of which would likely influence the formation of Herschel, Mimas's giant impact, early on in the moon's history. And using simulations to look at Herschel's formation might offer some clues about the link between these two. Meanwhile, the largest of Dione, another Saturnian moon's impact basins, Evander, shown at the bottom right of this image, possesses highly relaxed morphology relative to other large basins in the Saturnian system, which has led researchers to suggest that a subsurface liquid layer persisted during its formation and cooling. Well, if we simulate the formation of Evander, we might be able to pin down the thickness of that ocean relative to potentially ocean freezing over Dione's lifetime. And lastly, Tethys. Tethys is a fascinating moon because it has this giant impact basin, Odysseus, which we can see here in the upper right. And it also has the massive canyon system known as Epicasma, which is here. Now, these two large geologic features on Tethys have been proposed to be connected to one another. It's been suggested that Odysseus could produce Tethys. Sorry, it's been proposed that Odysseus could produce Epicasma, but attempts to age date the system and previous simulations have left their potential relationship uncertain. I believe with my new techniques and updated simulations, we can go back in and investigate the potential structural link between Tethys' largest impact basin and its largest canyon system. And those are just a few of the other basins out there that I'm planning to explore in the future. Thank you for attending today, and feel free to contact me after this talk with any further questions. My contact information is below. Otherwise, I am happy to answer questions now. Thank you.
Thanks so much, Adine. I know it's sometimes hard to get a sense for the audience appreciation during these talks, so if you enjoyed the talk, please let Adine know in the chat. So we have a couple questions to start off. Paul Schenk asks, is the non-sharp rim real or an artifact of the modeling?
Oh, the non-sharp rim of Sputnik Planitia, you mean? I hope. Well, when impact basins get quite large, their rims become also large distributed features. So, I mean, the rim of Sputnik Planitia today, as identified by you, is quite a broad distributed feature. So we're interpreting the broad rim that we get as largely associated with that. That said, the sharpness of the rim is something that varies predominantly with varying the thermal gradient. So when the ice shell is cooler and a bit stronger, the rim is sharper. And one of the other things that we're looking at doing is trying to do some finite element work, looking at how the basin cools and relaxes over time and how that does change the rim's shape, because that might determine to a greater level of detail which one of these is really accurate for Sputnik Planitia today.
Walter Kiefer asks, is the inferred thermal gradient from the first half of the study consistent with the inferred ocean thickness from the second half?
Yes, actually. So I will note that thermal gradient in the ice shell really doesn't affect antipodal focusing at all. Small changes, these are relatively small changes in the thermal structure of the ice shell, don't really change how stress waves go from one side of the planet to the other, particularly in contrast with the impedance contrast between materials. But what I find is that the thermal structures, the ocean thicknesses that best reproduce Sputnik Planitia in the near field that I showed you in the first half of the talk are consistent with the ocean thicknesses that best produce antipodal deformation in the second half. I did test whether thermal structure did change antipodal focusing, and it really is, it's too fine a detail.
So, Sean, let me chime in.
Sure.
And I hope you can hear me. There's a mower in the background, so I'll speak loudly. The point I'm trying to make, Adine, is not the effects of the temperature gradient in the ice shell on the seismology, but your ice shell, excuse me, your ocean is basically bounded on the bottom by the core, which you have a fixed size, I think.
Yes.
And it's bounded on the top by the thickness of the solid ice, which is controlled by the thermal gradient. So in effect, the thermal gradient tells you how thick the ocean is as well, because you've got a fixed core. And now, I guess the variable is there some antifreeze in the ocean? But
yes. When we consider ice shell thickness and ocean thickness, I tried to articulate this, may have not done the most clear job. We basically assume zones of stability for an ocean thickness associated with a variable level with varying degrees of thermal gradient in the ice shell. So for each ocean thickness, there's a range of potential ice shell thermal structures associated with it, and that range is based on how cold an ocean can be and still survive. And that range is itself based on whether there's antifreeze in the ocean, which is possible, though unlikely to be very high, but also based on theories that you could have something like Suichi Kamada and Francis Nimmo suggested that you could have a layer of methane clathrate in between the ice shell and the ocean that effectively allows you to have both a really cold ice shell and a relatively warm ocean at the same time.
Okay, if you add additional chemical constraints, then
Yes.
it would. I'm working from the context of it's mostly ice, and therefore the temperature is the temperature. But if you add enough, I guess if you add enough chemical complexities, you can decouple it. Okay, thanks.
Yes, yes. Though the chemical complexities of Pluto's ice shell is something that really is unconstrained, particularly how they would affect mechanical properties.
Sure, and I do this. I come from the perspective of the inner solar system, so I don't even know what the range of complexities are. I just as a modeler, I had to ask the question. Nice job in the talk. Thanks.
Thanks. Yeah, well, it sure would be nice if we had an equation of state for nitrogen ice. That would be great.
Okay, thank you.
Paul, I was just clarifying about the rim, whether erosion rounded a scarp to a distributed feature or whether that was a primary.
I'm so sorry, you cut out.
Oh, yeah, I think there's something going on with my microphone. There was a comment on that earlier. I apologize for that.
I would love to hear what you want to say.
Well, Paul Schenk was clarifying that he was asking about the rim, whether that was the effect of erosion rounding a scarp or a primary effect.
Ah, yes. Okay, that makes a lot of sense. Thank you, Paul. Yes. Well, we find that predominantly, I would love to send you more pictures of my results, but we do find that the rim is much more rounded because the basin is so large. And that's just an effect of the overall basin size and the massive amount of deformation that occurs in the ice shell during basin formation. So it's still distributed over like at minimum tens of kilometers, but I do also fully believe that erosion has significantly altered that rim structure.
Bill Minarek asked, what sort of temperature rise would be expected from the energy deposited in the serpentine antipodal to Sputnik?
I'm not entirely sure what you mean. So do you mean the change in temperature at the antipode?
I can jump in. I was just curious to know what sort of, so there's a lot of energy that causes the particle motions that you showed us in the GIFs, and that energy presumably is dissipated as heat. Is that enough to melt the rock? Is it enough to keep the ocean liquid a little longer?
Most of the heat from impact is actually retained in and around the impact site. So the initial impact does warm the ice shell quite significantly, but that's not a huge effect at, say, the antipode. One possible influence that Sputnik Planitia could have is that it warms not just the basin, but also the area extending about, depending on the pre-existing thermal structure of the ice, you can warm the surrounding ice outside of Sputnik Planitia for about 100 to 200 kilometers. So Sputnik Planitia, the formation of Sputnik Planitia basically deposits a large heat load in one specific area of Pluto. In terms of sustaining the ocean long-term, Sputnik Planitia cools off pretty fast, geologically speaking. So finite element simulations preliminary work suggests that it takes, assuming just heat conduction, it takes up to 200 million years, which is relatively slow relative to the lifetime of Pluto and hopefully its ocean. I hope that answers the question.
Pat, yeah, if you have a question, you can go ahead and unmute.
Yeah, hi Adine, this is great, as usual. Yeah, as you're probably aware that my group, including Oliver White and Paul Schenk, have been working on modeling of the Sputnik Planitia Basin and how that tells us something about, like, say, the ice shell of Pluto. And, we had a paper and we just got some very, we got some really useful, helpful reviews that pushed us in a good direction. And I ended up learning a lot from the whole project, including the revisions that we had of our paper, which we hope we can get in and get published soon, that changed my thinking about how thick the shell might be. To thinking that it could be pretty thin. And I see that sort of trend going in your results too, that the shell, that there may not be all that much ductile stuff going on. That whole insulation idea from Kamata and Nimmo, making it possible to preserve, it makes things more consistent with my picture, the results from my modeling as to how thick the shell could be. It also makes it easier to preserve things like the mascon if you don't have that ductile part. I was just wondering if you could comment on the evolution of your thinking about how thick the shell is over time, and just recapitulate, maybe you probably already said this, but where your results have pointed you in terms of that.
So it's definitely something that I'm still actively thinking about, because while I was very pleased to note that when I was looking at both the formation of Sputnik Planitia and any possible antipodal features, I found that both were consistent with a relatively thin ice shell. So I was generally pretty happy with that. And I do still largely think that it has to be the case. But the primary wrinkle in my thinking about ice shell structure is actually taking a look at Bernie and thinking about how you produce a multi-ring basin in that same ice shell. And it's not so much ice shell thickness that's the main factor, though. If you make the ice shell too thin, actually, it's very difficult to produce a multi-ring basin. I mean, well, what you get is what you see in multi-ring basins in the Galilean satellites, and not Bernie. So I do think the ice shell is thin, but I think it's an open question what its thermal structure might be.
Mhm.
Yeah.
Well, that sounds like the Bernie work, which I was not aware of before, may be the key to unraveling this. So I look forward to hearing more about that in the future.
Thank you.
Fantastic. Well, I don't see any more questions in the chat, and it's 4 o'clock. So I want to thank everyone for coming to the seminar this week. Thank you so much, Adine, for giving this talk. It was really great. There is no LPI seminar next week. However, if you are interested in icy planets and the dynamics of that, I would love to invite you to the Modern Brines Conference being held at LPI all next week. No registration deadline, and the focus of the conference is an integrated look at astrobiology, chemistry, and geology of brines as we know it throughout the solar system today. And it as the first part of our LPI's new initiative of brines across the solar system. But if you're interested in joining that, please take a look at our brines across the solar system website and sign up. Other than that, we will be in touch when we have our next FBI seminar scheduled. So thank you so much for coming, everybody.
Thank you for having me.
Have a great afternoon.